This is not physics, because physics is things that preserve energy. So let's do it as a piece of physics. We would like to find blocks, but we would now like to find something that's Hamiltonian, energy conserving, can be turned into quantum mechanics. So the simplest example is to look at kicked rotor. And we will redefine, we'll do it in two ways. The usual one, forward in time, and how the condensed matter crystallographer thinks of it. So traditional situation is like this. You have something running on a circle, and it's not losing energy. There's no friction, and you kick it. And to make it a discrete time problem, you kick it at integer units of time. That's called Taylor-Chirikov-Green standard map. And it's a Hamiltonian system. So on the left-hand side, you have time derivative of the position, discrete time derivative. Right now, time step is 1, equals to the momentum, and time derivative change of momentum, which is called acceleration, equals the force. And if you take sensible force, sines, cosines here, you get beautiful pictures. But if you're very naive, you say, well, simplest force is the one of the hook, right? I push and I get a linear response. If you do this, then the thing on the right-hand side just becomes a linear problem, except remember modulo 1 makes it nonlinear. Now you don't want cats to accelerate to infinite velocity, so you take modulo 1 also in acceleration. And that puts the problem on the torus. It's called continuous automorphism on the torus, or cat map. And you can write it as initial state, it's 2 by 2, two-dimensional, goes one step forward in time. Many choices of this linear map. Convenient one is this one. And so the only thing that matters, determinant in a phase space is 1 because of Liouville volume, so you only care about a trace. And the trace is, if S is larger than 2, you find out that this is hyperbolic system rather than elliptic. What we've been taught was the Hooke law. You press something, it pushes back, and you get oscillations. In mechanics, these oscillations persist forever. Now we do something that's pretty simple, but people don't tend to do it. If stretching is larger than something, then actually this thing gets unstable and precisely develops hyperbolic rather than oscillatory eigenstates and eigenvalues. But because in your torus, whatever you perturb comes back to you. So cat, you might not like it when you read it in books, but it's the simplest possible thing in mechanics. Harmonic oscillator is the simplest thing to understand mechanics as oscillations. But if states are unstable, then you have cat. There's nothing more fundamental than that.